Bam, bam, bum. Bam, bam, bum. Bum, ba, bum, 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 ba, bum, 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 bum. Ladyada from the desk. Bum, ba, bum, 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 ba, bum, bum. Did you see that?
What?
What's the British intelligence agency? MI6?
MI5?
MI5. They said that Q is actually a woman. Did you see that?
Yeah, I'd be
That's
cute.
cool.
I make all sorts of cool shit.
I know.
Cell phone jammers and like.
No, I think I was
Pen
thinking.
bombs.
Yeah, yeah.
Yeah.
Anyways, let me I'll start this other stream.
Okay.
Yeah.
All
Anyways,
right.
yeah, if you move around.
Do 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 do.
Bum 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 bum.
Okay.
Bum bum bum.
Well, we actually aren't doing spy stuff.
Bum
Well, I guess
bum
maybe.
bum. Bum bum bum.
All right, let's get on with it.
Okay. Hi, Internet. It's the desk of Ladyada. With Ladyada.
Thanks, Mr. Ladyada. That's right. It's me, Ladyada, here at my desk with a Saturday night, drinking a beer, chilling out. The world's exploding. We're here and we thought this would be a good time to maybe teach some people electronics. So we were going to have a video stream, a FUNdaMENTAL Saturday. Is that what you're calling it?
Yeah.
FUNdaMENTAL Saturdays?
FUNdaMENTAL.
A FUNdaMENTAL Saturdays video, and because people really liked.
all in your mind. Fundamental Saturdays.
Because people really liked the videos that we did about a week ago about PDM versus I2S microphones. And on the weekend, I had a little bit more time to do longer videos. So I thought, let's do a video and we'll talk about capacitive touch and explain how capacitive touch works and how you can build your own capacitive touch sensors. Because they're really neat. And with microcontrollers, it's super easy. So, hey, can you go to the overhead? So in case you're like, what's capacitive touch? This is a circuit playground running one of the demos I have. And as you can see, when I touch these pads, when I touch the exposed circuit pads, the LEDs turn red. Capacitive touch. It's basically a way to have a signal or a button where you don't push something in. It's not a mechanical switch, it's an electrical switch. Just the action of touching it activates it. And you can see capacitive touch on some devices around the house. You know, we have capacitive touch screens, which are basically a capacitive touch sensor but on a grid, and they have interpolation to do like full XY. But for now, I thought maybe we talk about just what does it take to do, you went away, to do simple touch detection, human touch detection. And this lets you do stuff like, you can have metal devices that you touch them, or if you have it's attached to a banana. When you touch the banana, something can happen. So it's a good way to add a cool interactivity element. But it's also a good way to add an inexpensive input because capacitive touch is way cheaper than an actual button. And although they don't like getting wet, like they don't work as well when wet, they don't oxidize the same way. You can put a glass and then the button goes through the glass. You don't have to worry about them getting dirty or wearing out like they do mechanical buttons. So there's nice reasons for using capacitive touch. Yeah. Okay, so that's what capacitive touch is. So before we talk about how capacitive touch works, I thought I would talk about some of the fundamental electronic concepts that make capacitive touch function. Like what is the basis by which we can do this? And so I brought my handy whiteboard. Nice whiteboard. Oh, can you? I guess we can.
I feel like can I play a video real quick?
Yeah, sure.
Okay, because you talked about capacitors.
Well, I haven't talked about capacitors yet, but I'm going to.
Okay, then I won't play the video
In a moment.
Okay,
so how about you wait?
What do you want to do here?
Oh, that's cool. This is kind of.
Yeah, it's because you put.
The shade.
Yeah.
Okay, neat. Okay, so a lot of times when you learn about electronics, you learn what's called the water analogy. I'm so about the water analogy, but it kind of makes sense. Let's say. In this case, a lot of times we say a pipe is a resistor. So, this is a pipe, like a faucet. And the width of the pipe is resistance. So if you have a water tank, we're in New York here, so we actually get water tanks. And this water tank, it's a battery. Right? It's something that holds a lot of water in it. And the thinner the pipe, right, the tougher it is for water to get out, the less water that comes out. Water current, it's kind of an analogy. And the water that comes out here in drops, this is the current that flows through the resistor, the pipe. And if you have a big fat pipe, the water comes out really fast, right? If you have a very thin pipe, the water drips out very slowly. So high resistance, thinner pipe is more resistant to the water coming out. And let's say, we have a bucket. We have a tub down here, bucket. I don't even put a handle on it. And the water fills up the bucket, slowly, drop by drop. So this is the mental image you want to have. When the pipe is very skinny, there's a lot of resistance, it takes a long time for the bucket to fill up. Drip by drip by drip, slowly, slowly, slowly. When the pipe is really wide, it fills the bucket really fast, right? The height of the water goes up much faster. Like every night I fill up my humidifier. And if it takes, if I want to do it slowly, I use the sink, right? I open the faucet and I fill the humidifier bucket and I'm sitting there and I'm waiting and I'm waiting and waiting. It takes like a minute. If I want to go really fast, I go to the tub and I open up the tub faucet. It's a huge faucet, can fill up a tub very fast, and I'm done in like 5 seconds. So the width of the pipe determines how much fast the water comes out, and then how fast the bucket fills. So let's say you have a way to detect. Let's see, you have your eye. Kind of a creepy eye. You can tell when the water hits a certain level, right? And you can time it. You have a stopwatch, and you can time it. You can say, okay, starting from an empty bucket, how long does it take the bucket to get full up to this point, depending on the size of the bucket and the width of the pipe. So if you have a really thin pipe, again, it's keeping the bucket the same size, it's going to take longer. Wide pipe, less time. But also, if you think about it, let's say all you're doing is measuring the height of the bucket. Well, if you can change the size of the bucket, that also determines how fast it's going to fill, right? If you have a super, super, super wide tub, it's like super big, like this, then it'll take longer to fill the bucket with drops of water than if, say, you have like a super skinny bucket. Let me clean this up a little bit. So let's say you have like it's kind of like a tube even. Maybe it's like a pint glass. The drops come in, and you're still looking to see when it hits this line, it's going to be faster, right? So there's 2 ways you can adjust how long it takes to fill the bucket. Either make the bucket thinner or wider, or make the pipe thinner or wider. All good so far? Any questions?
No.
Okay, good.
Keep going.
It's pretty simple stuff, right? You think about it. Just think about a bucket and a pipe. So the capacitive touch sensor, actually, this is exactly what you're doing with capacitive touch. You're measuring the voltage as it rises in this capacitor. The bucket's actually a capacitor. And the width of the pipe is a resistor.
Lady's Ohm's law, which I thought was funny, and then someone said Samsung had a small bucket, but a large pipe equals boom.
Yeah, well, you gotta be careful.
Yeah.
The bucket can overflow. So the capacitor is what we're measuring, and basically there's actually another trick. If you know like how many liters per minute this pipe is letting water in, you can actually figure out the size of the bucket, right? Because if you figure out how long it takes to fill up to, say, this mark, you figure out how many liters that is, then you can back calculate the size of the bucket just by knowing that, if this is 1 liter per minute, and this is the 1 liter mark, and it takes 1 minute, that's, it all matches up. So it's kind of the same idea, except instead of water, we're going to use voltage and current. So let's go to the computer.
Okay.
So I'm going to use computer.
Yeah.
So I'm going to use an Arduino basically to help write this code. You don't have to use an Arduino. It's a handy tool that I have. It's pretty simple actually. All you want to do is you're going to have the pipe, the output. Right, we're going to call this the touch out pin, and I'll make that 13. And then you want to have the pin that's basically measuring the height of the water in that bucket, which is going to be the touch input pin. And I'll show you how this works out. But we just want to define these. And then let's start by, we'll just set the touch out pin to an output, because water current is coming out of it. And then the touch in pin, let's make it an input. Again, actually nothing's really going to happen with the touch input yet. And then we're going to turn the faucet on and then off, basically. Set this high. And then set it low. And, we're going to give ourselves a little bit of time delay between this. So give myself, 10 milliseconds. Okay, this is like super simple. Just all right now we have is a pin that's going high and then low, once every 10 milliseconds. And then we'll noodle around and then we'll use the microcontroller to measure that capacitance. But we have to get this going, upload it to an Arduino. So we're going to do that. I'm going to unplug this. Okay, so it's done uploading. Okay, so let's go to the overhead cam. Okay, so we have this Arduino basically, and let's look at the, we're just going to click the
I'm going to make a square so you can do it at the same time too later.
What do you mean, like this?
Like, no. You know how I did this round circuit playground before? Do you want me to make a square?
Oh, no, that's fine. Yeah, I think we're going to have to flip between the oscilloscope and this. So this is my, my oscilloscope probe. And I've just got it wired up, so it's looking at pin 13. So let's look at pin 13 really fast on the oscilloscope. And we'll bounce back and forth.
Okay, you want to do which now?
Oscilloscope cam?
Scope cam.
Yeah.
But an upgraded scope cam too.
We did. We upgraded scope cam. So this is a scope cam, and I'm going to just zoom in here. So you just see up, down, up, down. That's all this pin is doing. So now we want to add that pipe and that bucket. So let's go back to the overhead.
Why aren't you using MicroPython for this?
I'm not using MicroPython because it would be too slow, and a lot of people would be using. You could do it with MicroPython, but it's a lot slower. You actually need pretty fast timing. I'll show you how fast the timing is if you want to get good response rates, because the resistor size would get very big, to match up with like the time constant. That's like the long story. So when you do capacitive touch and MicroPython, we actually have a little helper to help you out. Okay, so we're at the, we're back here. So let me grab, 1 second, I gotta get some parts here. So let's grab a 10K resistor. We're just gonna start with a value, and we'll just mess with it until we get what we like. So let's say, we've got a 10 kilo ohm resistor. And then this is that pipe, right? The water coming out here, and here's the pipe. So let's, we'll check the input here. And then we want to fill that bucket, right? So we'll take a capacitor.
When can I show a video about a capacitor? Might Sparky different.
Well, let me just finish this one demo.
Okay.
And then,
Everyone, if you haven't seen Sparky the Blue Smoke Monster, you're in for a treat because you will soon.
okay, so this is a 100 microfarad capacitor.
Why 10 KO? Why?
Because the popular value, we'll start with that, and we can, go up and down, right? 10K, most people have a 10K. So the bucket goes from the output of that pipe to ground. And then we're going to put another probe here. And Okay, so actually this is a little too slow. So this is actually a good demo. So let's look at the oscilloscope. So there's actually, what's interesting is it's actually just averaging it out, because it's actually, you know, an RC, when you have that RC, it actually levels out the signal. So let's do something where we like super slow down that square wave. So instead of every 10 milliseconds, let's make it 1 second. So give me a moment and we'll slow it down so you can see it on a big scale, and then we'll see shrinking it down. Okay, so now that square wave is super slow. But what's nice is you can see the bucket filling and then emptying. Filling and emptying.
That's cool.
This blue voltage here, actually I should do it from, sorry. So this yellow square is the pipe filling the bucket and emptying the bucket. It's turning on the current and then it's draining it. And then this is the bucket filling and then dropping, filling and dropping. So you see it takes quite a while. Like this is happening on a second by second basis. The capacitance that you want to measure when you're a human, the capacitance of the human body, is nowhere near 100 microfarads. It's a lot smaller. So let's mess around with making the bucket thinner. So we're basically mimicking the human body. We're gonna mimic it by using a smaller capacitor. So let's go back to the overhead.
I like 10K before it went mainstream.
10K is the most popular by far. So
I
we had a 100 microfarad bucket.
I liked it before everyone else did.
Okay, so now we're going to use a different capacitor. Do we need a capacitor?
Is it time?
It's time.
Okay, here it is.
Okay.
Capacitor. Capacitor. You know, you need a capacitor. Capacitor.
Ain't
Okay.
no other place on the internet doing stuff like this right now.
Thank you. So the previous bucket actually is bigger, right? This bigger, fatter bucket, 100 microfarad. Now we're using a much smaller bucket. This one is 1,000 times smaller in capacitance. It's or capacity. It's a 0.1 microfarad. So let's try this. So we'll put this bucket in place, and let's see how this goes. Okay, so let's go to the scope cam. Okay, so now when you see the scope, you're actually like, well, it looks like the bucket fills instantly. That's because, you know, it fills up so fast. So we'll have to zoom in. Let's zoom in. Oh, you know, the scope doesn't like to trigger. You can see it triggers a little bit, but it's a little bit, it doesn't like that it takes so long. So we can go on normal trigger. Let's go normal trigger. Okay. So now you see, you still have, this is that faucet turning on and current starts flowing. And then here you see slowly the bucket fills. It's a lot faster now, but it's still kind of slowly filling up. So we're getting closer to what we want to detect because, again, the human body, the capacitance of the human body, it's a bag of water. And so it has, does act like a very bad capacitor. If I touch this, you can't really see. It might, the capacitance of a human body, I think it's like 100 or 200 picofarads. It's a lot less than this. It's like 100 times less. So we want to make this even a smaller bucket, and maybe you can make, to slow it down, you can also make the pipe thinner, right? So we tried making a smaller bucket, but also making the pipe thinner will give us a longer timeline over which we can see differences. So let's go back to the overhead. So I had that 10K resistor. Well, I'm going to take that out, and I'm going to put in a, this is like a 900 kilo ohm resistor, so 10 times more resistance. So it's a 10 times skinnier pipe. And then I'm going to keep this capacitor for now.
There is a question.
Yeah, it's a question.
Why doesn't it fill linearly?
Ooh, that's a really good question.
Ooh, good question, Power Piglet.
That's a really good question, and it has a little bit to do with calculus, but it's because it's the difference of the voltage, so it fills up very fast. How do I explain it?
So think of the bucket's bottom being smaller than the top.
Yeah, but that's not the reason why it happens. It's basically due to calculus. And I was actually thinking, like, should I explain RC constants?
The rate of the fill is proportional to the excess voltage, so it turns out to be an exponential law. And
yeah,
then, Micah suggests we need a differential equation puppet. I agree.
We do.
I'm working on it. It's just complicated.
It's basically the pressure changes, basically. This is the thing, I didn't want to talk about it because it's like, I don't want people to think like, I need to know calculus to do this stuff, because a lot of it is very experimental.
Rubber band analogy, some folks are saying. It looks like it fills faster at the start and slower at the end.
Yeah.
Due to the nature of repulsive forces of the charges. Oh man, we're into string theory.
I know, this is tough. Well, let's finish, you know what, we'll do another fundamental Saturdays. Maybe we'll talk about...
It's the same way a bucket drains faster at first if you have a hole in the bottom.
No, I mean...
Keep going.
I'm going to keep going.
Keep going.
This is actually a tough one. This is the problem with the water analogy. It actually, the level of the bucket would be linear, so it's like you think of it a conical bucket, but the fact is a capacitor isn't conical, not in that way. But it's actually, yeah.
Okay.
Anyhow, so but it's a good question. It's such a good question. I don't have a good answer for you right now. But maybe we'll talk about RC constants, time constants, and why this occurs in a future video. Okay, so. But for now, it curves up. It takes a longer time to fill later. It fills up fast, and then it takes a little bit longer. Okay, so let's go back to the oscilloscope. So now you see I made the pipe skinnier by 10, so now it actually takes way longer to fill. So now I can zoom out, and then you can see like, wow, so this is taking a lot longer. Let's see if now my finger makes a difference. Might not. Still doesn't. No, because the 0.1 microfarad is actually still affected. Let me see if I can swap out. I don't have super teeny capacitors with me. I don't think I need. I have a 20 picofarad. That's way too small. Let me try this. Do I have a 103? 1 second. I'm reading a little. You can read the values of a capacitor, but they're super small. 103, 103. Let me try my 103. See if that makes a difference. So as you see, that just sped up. So let me zoom out a little bit. Let's see if this makes a difference. That's some noise, but let me put it on auto. Hold on, let me have it go up and down a little bit faster. But it might be, I don't have a capacitor on hand. Yeah, look at this is 20 picofarad, which I think is too small, but I can try it. Okay, so now you see actually it's, actually I'm doing it a little bit too fast. 10, I just see more noise. Let me try,
You can get a couple picofarads per inch of twisted wire.
I know, but I have a 20 picofarad cap here, so let me see if this is...
And someone says it's like filling a balloon, maybe not a bucket. Maybe that's...
Okay, so now, can you go to the overhead really fast?
Yeah.
Oh yeah, this makes a big difference.
That's your show.
So now I have a 20 picofarad capacitor, so like, this is like from 100 microfarads down to, this was a 0.01 microfarad, down to a 20 microfarad. Now if I had 200, that would be perfect, because that's kind of on the range of a human. But 20 picofarad, it doesn't matter actually. You can measure any capacitance as long as you have a big enough resistor and a fast enough oscilloscope. Okay, so back to the oscilloscope. What these capacitors I got a whole bunch of them. Okay, so you see I just zoom, whether you zoom in or zoom out, you get that same waveform, which is kind of nice. You get that same, the capacitor fills up slowly and then kind of reaches the top, and then it follows the square wave rising. It just has a little bit of a delay. See, it's kind of, it starts filling immediately, but it slows down a little bit as it gets to the top. So what's neat about this is when I put my finger on the capacitor now, I can actually, let me trigger on, hold on, trigger on 2, a little better. You can see that my finger actually makes a difference.
Bag of mostly water, press.
Yeah. It gets a little, it's tough to know because it's, see if I can get it to trigger a little nicer. No. Let me go back to triggering on one. One moment. Yeah, you get a little bit of noise, but you do see that the shape of it gets flatter. Let's zoom out. It takes a little bit longer for it to, see, it goes down. It squishes from being pointier to being rounder. So that's actually what we're detecting, by the way. Right? The amount of capacitance makes it take longer to fill up. So actually, I can remove the 20 picofarad capacitor altogether. And so you actually see there is a little bit of capacitance naturally. It doesn't follow perfectly because there's a little bit of capacitance on the breadboard and there's a little bit of capacitance on the pin. So you're never going to get a perfect square. Like it's never going to be instantaneous. But then, yeah, as I add my finger, you see it gets rounder, takes longer to fill. And that's what you're detecting. So is there a way to go to the, I can't show both, but I can show the overhead.
No, that's what I was saying before. Do you want me to? I can make a thing that shows both.
You want to try to do both?
Yeah, sure.
Yeah, I guess
I think I can do it. Hang out.
Okay.
So you want the scope and that at the same time?
Yeah.
Okay. So put the metro more over to this side. Yeah, sure. Okay. And then I'll do some things.
Okay. Let's try.
Yeah, we can try. Don't worry.
Okay. This sounds good.
Yeah, it'll work.
All right. Look, we're doing video science here.
No one does stuff like this. So what if I were to go like this?
Yeah, like that.
And then
Like that.
like that, yeah.
Like that.
And then like
that.
that.
And then like that.
Wait,
Like that. Yeah.
like that, right?
That's great.
Okay. And then like put that like where like right
Yeah,
here.
yeah. That's good.
Like
yeah,
right here, that's what you want,
that's good,
right?
that's good,
You can
that's
move
good.
the metro a little bit.
Yeah,
if you
yeah,
want. Okay. All right, folks, there you go.
Okay. So now we have a triple view. So the oscilloscope, you can see when I touch, I'm literally touching the end of this resistor. You can see it gets that wave gets flatter because it's taking longer for it to fill because it's the charge is flowing onto my body. It's kind of cool. I'm storing charge. And this is basically that, and what's cool is, somebody at some point, they were working on circuitry and they noticed that when they touched it, it changed. Like, if you have an oscillator or you have an op amp and you have capacitance that's somewhere in your signal path, you're bringing in noise, but also you're adding capacitance, which is sometimes why engineers notice, like, if you touch something, it stabilizes. That usually means you need capacitance. It's a trick sometimes if you have like an op amp circuit and it's oscillating or it's not oscillating, always doing whatever you don't want to do. You just start touching things and seeing if that extra, 100 picofarad capacitance that is on your body changes your signal and makes it stabilize. Don't do that with high voltage circuits, but you can do it for 5 volt circuits. You can just touch them. But it's something to think about. Sometimes you want this and sometimes you don't. There's a saying. It's like if you have a circuit that is strongly affected by temperature, it's really bad unless you're building a temperature sensor, right? So it goes both ways. If you have something that's affected by a phenomenon, it can be a phenomenon detector. So this is a touch detector now. You can see it changes, the capacitance changes the wave. So let's go back to our computer because now we can actually measure this. So what we're going to do is, we had that touch output pin, that touch input pin. Well, what we can do now is that touch input pin, what we'll do is we'll measure how long does it take for that voltage on the capacitor to rise. It's very easy. So once you set the pin to an output, you say while digital read touch in pin, and actually you want to say while it's low because it's low and then it rises. So while it's low, and let's have like an incrementer called counter, and we just increment counter. And then once we get a digital read that's high, that means that we're done. The capacitor's charged up. We will print the counter number. And I just have to put in a serial begin here. All right, so let's upload this. See how this goes. Drink a beer.
What type of screen do you want to go to? The split one? When it gets there?
Yeah, let's go to, well, no, because I have to show the computer.
Okay.
So I'll just show the, I'll show the computer,
Okay.
the screen. Okay, so this is, well, oh, right, I have to wire up that pin. So let me get another wire. And then I'm going to connect the output, the other side of that resistor, to pin 12. Okay. So the reading is, it just says like 5, 6, that's about the number. So again, there is some natural capacitance of the pin itself. Every microcontroller pin has about 5 to 10 picofarads of capacitance. The breadboard has the capacitance, the wires has the capacitance. So again, it's not going to be 0. It will take a couple counts for it to rise. But when I touch the pin, it goes up. Actually, you know what? Let's use the plotter. Yeah, plotter time. So it's around 6, and then when I touch it, it goes up a lot. You'll notice that it's a little bit wavy, like I'm not getting a signal, a single reading. That could be because of like there's noise that comes in when you touch. Like I'm also a really good antenna. I'm picking up like 60 hertz noise, picking up like radio signals. So that does couple in. So what you have to do is you have to do some low pass filtering on this or peak detection, depending. You can also, I want to make this maybe a little longer. Let's try that. One moment.
And this is one of your favorite features in Arduino IDE, right?
I love the plotter. Look at how
Yeah.
nice it is to show, because it's like, how do you show that it's noisy without this?
Yeah, we're working on some Circuit Python stuff, so maybe Mu or something else will have a plotter.
That's only too slow.
I think can microbit? There was something you could do with microbit that like plots, right? I thought we could do data
I
logging.
don't know if Moo has a plotter. I know that we talked to
No, Move
N20.
doesn't have a plotter yet, but I saw something with microbit that you can do. Anyways, we're gonna we'll have something.
Yeah.
Alright.
I love plotters. Okay, it's a little bit faster. So yeah, there's a little bit of noise, but you know, you can tell like it's very clear when there's signal and when there isn't. So you do have to do a little bit of filtering on it. So maybe let's do a couple of readings. We'll just add on to this. So define num readings. I'll just say 10. I can always change it later. For R equals 0, R smaller than num readings. And then we can just sum all the counts up. Let's see how this goes. Actually, let's do
Chris Young's in the chat. Hey, Chris.
Hey, Christian. Big capacitive touch. Okay, so let's try 5 reading, and we'll just sum the counts up. So it'll do some very basic filtration. We'll see how that works. Okay, so it's a little bit cleaner now. I mean, you can do this forever. You can mess with the readings and blow past them as much as you like. You can see, you know, when I touch it, the sum of all the readings is between like 300 and 400. When I let go, it goes down to, you know, like 20 or 30. And this is pretty much, that's it. That's pretty much capacitive touch. That's what you're doing.
You just made capacitive touch.
Oh, you just make capacitive touch. It's that easy. So the reason I'm doing this video, I'm wondering, like, why talk about this video? Well, I showed you capacitive touch on the circuit playground. So let's now go to the circuit playground.
Oh, you want to show the code for a sec?
Oh, yeah.
Yeah, move it over to the right.
Oh.
There you go. Same code.
There you go. Sorry if it wasn't visible.
Yeah.
Right now, the only thing I added recently was I have a loop, and I just take 5 readings of the time it takes to charge the capacitor, and then that does this very, very basic, because it's summing it over a long period. It does a nice low pass filter on it. Gets rid of a little bit of the variation because you're just summing it over a couple. And then you can mess with the delay, depending on the size of the resistor you're using and the capacitance you're detecting. And one thing to note is depending on the size of the thing that you're using as your like electrode, you may need to change your timeouts. Like if you have a gigantic metal chair that you're using for capacitive touch, you can, it's metal. The size of that will actually affect the reading because it is also, in a sense, a capacitor. So you may have to, sometimes you have to recalibrate. So here's a little faster, and then we'll do more readings. So you'll have to think about that. So when you get a capacitive touch chip, they basically do this. There's not much more than that, but they do filtering and they do some recalibration sometimes as well. Let me see if 15 readings improves it. Oh yeah, that's nice. There you go. So 15 readings. So you tweak your code. Like how many readings do you have to do?
Pressing it. Yeah.
Press
okay.
release. Press release.
That's what you're doing there.
Yep.
Okay.
Nice. Very fast. It can be very quick. It can be under a couple milliseconds. Okay, so the reason I was looking at capacitive touch and I wanted to explain it is in Circuit Playground and Circuit Playground Express. Let's look at the Circuit Playground to start. Rev B, open, board. We turn off layers.
According to some of our community, Eagle version 6 is safe.
Version 6 is what are these
Version
again?
6 is safe.
Okay, thank you. Let me turn on TW. Okay, so we have capacitive touch. I showed you at the beginning that Circuit Playground, and when you touch the outside, the LEDs light up. So there's capacitive touch going on here, and the way I do it is I have these resistor packs. So this is a resistor pack. And if you look in the circuitry, where is it? Up here. Every one of those pads has a resistor to a pin, 1 mega ohm resistor, and that's the same, the resistor I had on that breadboard, that's that one resistor that I used to leak the current into the capacitor, the bucket. So we have these 1 mega ohm resistors here, and they come in a 4-pack. Kind of nice, they're small, they're compact, you just place them, it's 1 pack, and it's like 4 resistors in a row. So you can see the signal, for example, this one goes into the resistor, and on the other side it goes into a pin, another resistor, another resistor, another resistor. So you need one resistor per sensor, but no biggie. We just use this 4-pack here. But for the SAMD21, it actually has something interesting, which is a built-in peripheral touch controller. So instead of needing to have a resistor and a pin to do that toggle, it actually has that circuitry built into the hardware. And it can scan all the channels for you, and it has basically built-in hardware support called Q-Touch. This is like Atmel basically has capacitive touch built into. It's very inexpensive to add the circuitry. Again, they have a resistor and a pin, and it just like measures the charge, and it just measures how long it takes. So they have this circuitry in here already that can do self-capacitance, which is like single pin, or grid capacitance. So when you have X and Y's, and it can actually do a full grid for you, which is kind of neat. So what I wanted to do is, in the Circuit Playground Express, because the SAMD has this native hardware support, I can maybe drop those resistors. Not because of cost. The cost of them is very low. It's only like 3 cents for a resistor pack. But it saves me a lot of space. And if I can get rid of that space, that routing, having to use that extra pin and use the hardware capability, that can be really nice, because you can see it has like an adjustable resistor, it has input control, it has the filtering for you. It can even give you an interrupt, so you can have an interrupt on touch. So having all that done for you in hardware, it can be really, really nice. Like much better than having to do it yourself. And it might be even faster. Also, you can do it in the background. Like right now, as you've seen, there's a busy loop. There is a loop where you're sitting here and you're like waiting for that pin to go high. You can't do anything else really until then. I mean, you could have 8 interrupts on for each pin, but it's a kind of a pain. Having the hardware handle the touch controller would let me not have to deal with this. I could just have it happening all the time, and then I can ask the microcontroller, hey, when you get any touch, let me know instead of me having to constantly check the pin for whether it's dropped higher or risen up with that capacitive voltage. So it's still good to know how to build your own capacitive touch. I had to do it for the AVR version of Circuit Playground because that doesn't have hardware support. But for the SAMD, adding hardware support can be pretty sweet.
Here's a question. Is this the same kind of value you get from the Circuit Playground .read cap?
.read?
Circuit Playground .read cap. You see?
I don't know what. I don't understand.
.read
Oh, the
cap.
value?
Yeah.
The value is it's valueless. It counts. So it depends on how you're doing it. The capacitive touch library we're using for Circuit Playground actually is a little bit more optimized. So the values are going to be much higher because instead of using digital read, it actually does a hardware register read. So it's a little faster because it's reading the pin. So it gets better precision and accuracy. But it basically just does the read much faster. But you don't want to look at the absolute value. The absolute value has no meaning. What you want to look at is the difference. What's the count when you touch and what's the count when you don't touch? And then you would set like a range. Above this value is valid touch, below this value is not.
Next up, can this work on the ESP8266, ESP32?
Yeah, it can work on any processor. The thing to watch for is that if the processor has something going on in the background that can interrupt it, you want to just make sure you turn off interrupts when you do the capacitive touch sensing. But yeah, it'll work on any. The nice thing about this is it works on any microcontroller. If it has digital input, digital output, and you can turn the pin on and off and read the value pretty quickly, you can do it. Again, with CircuitPython, you can do it, but you have to give yourself a lot of time because it's much slower to read pins. It's not as fast because it's interpreted. So the trade-off is like you probably want to have a C helper to do that counting for you, so that you don't end up having like 2 or 3 counts, because you want to have like at least 10 to 20 counts or more, so you don't get too much variability depending on your electrode or whether it's humid or whatnot. So you want to make sure that you read that pin really fast. That digital read has to happen very quickly because it rises very fast. We can actually look at the speed. It's on the order of a couple, like 30 microseconds. It's very fast. So you have to, whatever you're doing that's reading it has to read it within about 100 microseconds. You can see down here, 25 microseconds per division, and it's about like 2 or 3 divisions. So 50 microseconds. You want to be able to read. If you can read at 1 microsecond per pin read, that's kind of ideal. You want to give yourself plenty of time. Some microcontrollers can read like much faster than that. So you just have to just read the documentation, depending on what device you're using. Like, for example, the Galileo uses a port expander, so you're not going to be able to do it.
Okay.
Yeah.
Is there anything else?
That's it. I mean,
Sure.
I think it's a pretty good demo.
That's the show?
Yeah. Everyone learned about capacitive touch.
Yeah. Okay, well, if you like shows like this, hit like and subscribe and purchase a kit or something. We'll keep doing a live electronic show on the internet. Someone asked, can you make a capacitive strip and measure based on position?
Yeah, that's actually a good question. If you have like an iPod, like an old iPod, you remember that you would touch it, you could swirl it around. Like, I don't know when they got rid of those, but they used to have the ring. That was actually like 12 or so individual capacitive touch. So what happens is that I can actually show this because it's kind of interesting how they do it.
To the whiteboard.
To the whiteboard, because it's a good
I'm
question.
going to do this.
Good benefits from a diagram. So you have your capacitive. I do want to actually build eventually a capacitive touch strip using this technique. But so like right now, you've got your microcontroller, right? And you've got that resistor, and then this is the output, this is the input, and then this is that capacitor, which is actually a human, right? So that when you have the electrode for that, usually you have an electrode that looks like, oh man, I totally used a Sharpie on my.
Oh no.
Yeah, I got it. I'll clean it up. I have
Will it come off?
Yeah, you just have to use acetone. I don't have any.
Yeah?
Whatever. This is fine. So usually the electrode. Yeah, I have like too many pins here. Dangerous. Usually you have an electrode and it's like a square or something like that. And so like literally when you touch the square or the button that activates it, or maybe it's like a circle. What you do if you want to have a row is you make these kind of chevron shapes,
Oh, that's neat.
right?
Yeah, I've seen that.
So you might have seen this
Yeah.
sometimes if you look if you take something apart, and then you have multiple capacitive touch pins, and then you sense the as your finger travels, you get a higher count from this, and then a higher count from that, and a higher count from that. So you basically measure the counts across all three, and then determine which direction your hand is moving in the position based on how strong the signal is from each of the three, or like usually it's 5 to 7 in the track. And then if you turn this into a circle, that's how you do a circular iPod connection, right? You just have one connection per. It's a little bit different for XY grids, but not significantly different. It's basically the same idea. You're just measuring as your finger moves. You can tell because you're moving over here. You're going to touch only a little bit of this and a lot more of this. And it just goes back and forth. And you just measure the signal strength.
Stargate. There are some suggestions on how to get rid of permanent marker on
I
whiteboards.
know,
They said isopropyl alcohol works. Also, you can use the Sharpie itself over the dried Sharpie and then wipe quickly.
Yeah,
Sharpie defeats Sharpie.
I know. Like I'll
Whatever.
I got isopropyl.
Look, we got tips and tricks.
I know. I'll clean it up before the. We have some cleaner.
Okay.
Also, a Simple Green I think does it.
Yeah.
I think a Simple Green can take off Sharpie. But
So I guess when you do whiteboard, I'll put a light like over there. So.
no, this is cool. I like it. It's like I'm in the Matrix.
Yeah.
All right. Are there any more capacitive touch questions?
No, that's it.
Okay. Cool.
Okay. It's spelled chevrons like the logo.
Yeah,
Yeah.
because it's a chevron.
Yeah, that's how
Literally.
you know. Okay, anyways. We'll keep doing this. We have some other videos that we're going to do. We have some stuff during the week that'll be happening, of course.
Mm-hmm.
Maybe we'll broadcast tomorrow. We'll see. But that is Desk of Ladyada
Okay.
for tonight.
Support us so we can buy some
We
more
need to get another
dry erase
whiteboard.
boards.
Yeah.
No, I'll fix this one.
Okay.
And dangerous.
Tonight's wisdom. Sometimes it's harder to get rid of the things that don't work than to start something new and different. Yeah.
Capacitor. Capacitor. You know you need. You need a capacitor. Capacitor.